I'm going to be talking about models of acids and bases today, specifically two models. The first model is called the Arrhenius model, and Arrhenius created this model to define what an acid and what a base actually is, and the model is fairly simple. So he said acids contain hydrogen. If the hydrogen is the cation in the compound, it's an acid. So what happens is when you put an acid in aqueous solution, aka you put it in water, it forms what's called a hydronium ion, because specifically that acid, in this case hydrochloric acid or HCl, donates its hydrogen to the water, forming that H3O+. So when water has an extra hydrogen, it takes on a positive charge because it has an extra proton attached to it, and then you can see that the chlorine is left alone as an ion in solution. So two things, acids contain hydrogen and it forms hydronium ions in aqueous solution. Bases, also very simple. Bases contain hydroxides as the anion in the compound. When bases are put into aqueous solution, they form hydroxide ions. As an example, you put sodium hydroxide, which is your base, into water, and they break apart into a sodium ion and a hydroxide ion. That's what defines an Arrhenius base. The Bronsted-Lowry model is a little bit more complicated than the Arrhenius model in that the reactants and the products have definitions. So just to start off, Bronsted-Lowry were two gentlemen that came together with this model, and they decided that acids are proton donors. And by proton donors, hydrogen, when hydrogen is an ion, it's basically just one proton, and because it's donated its electron. So we call it a proton versus a hydrogen ion. You can, either way, it's fine. Acids donate their hydrogen ions. Bases accept them. So as an example, you have the same reaction as I showed previous in the Arrhenius acid model. Hydrochloric acid plus water produces a chlorine ion in aqueous solution and a hydronium ion. So in this situation, if an acid is a proton donor and a base is a proton acceptor, that must mean we have one of each of those in the reactants. So for the Bronsted-Lowry model, you have to figure out what is the acid and what is the base on the reactant side. And in this situation, we know that HCl is the acid because it has a hydrogen up front according to the Arrhenius model. So you can kind of mix models to figure things out. So hydrochloric acid is the acid, and it's going to donate its hydrogen to the base. Well, if hydrochloric acid is acting as the acid, that means that water has to be acting as the base. You have to have one of each in this model. So water is going to accept that proton or hydrogen ion, act as the base because it's accepting, and form what are called conjugate acids and conjugate bases. Situation, the chlorine ion on the product side is acting as a conjugate base because it can't be an acid, it doesn't have a hydrogen. And then the hydronium ion, which accepted that extra hydrogen or extra proton, is now acting as an acid because it has the ability to then donate the hydrogen back into the system. So if you're going to go into reversible reaction, if you look at the products as your new reactants, the hydronium ion is able to donate a hydrogen back to the chlorine ion to then, in the reverse direction, form hydrochloric acid and water again. So we call those conjugates to differentiate them between the original acid and base. So the best way to figure out a conjugate is if it has an extra proton or hydrogen, it has to be the conjugate acid. And if it doesn't have a hydrogen at all, it has to be the conjugate base. In addition, acids produce conjugate bases, and bases produce conjugate acids. So what's up with the word conjugate? We just call them conjugates again to differentiate between their original acids and bases, and it's the result after the hydrogen ion has been transferred or accepted by the base. And then the conjugate base is the result of the acid having already donated its hydrogen ion. So here's another example. You have hydrobromic acid plus sodium hydroxide, and you can use the Arrhenius model sometimes to figure these things out. So because hydrobromic acid has the hydrogen up front, it must be the acid. Sodium hydroxide has the hydroxide on the back, therefore it must be the base. So we can define our reactants. The first one is an acid, the second is a base. And then to figure out the conjugates, you kind of just have to track the hydrogen. So if hydrobromic acid is the Bronsted-Lowry acid in this situation, it's going to donate its proton or hydrogen to the base. Therefore, if you look on the right-hand side, HBr becomes NABr, which has to be the conjugate base. And remember I said that acids produce conjugate bases. And the reason why it has to be the conjugate base is because it has the original anion from the acid, and it also doesn't have a hydrogen anymore. So if it doesn't have a hydrogen anymore, it can't be an acid, so therefore it turned into a base. And the bases always produce conjugate acids, so sodium hydroxide lost its sodium, and the hydroxide combined with the hydrogen from the acid to form water, and that is the molecule that has hydrogens, therefore it is the new acid, so we call it the conjugate acid. All right. So in this situation, they're in a little bit of a different order. The water is amphoteric, meaning that it goes both ways. It can act as either an acid or a base. It depends on what you're putting in the solution with it. So this is being added to nitric acid. Nitric acid is going to be the acid because it has the hydrogen up front, which means that the water has to be the base. And if nitric acid, acids produce conjugate bases, well, if you track over on the product side, that NO3, which came from the acid, has to be the conjugate base because it no longer has a hydrogen, therefore it turns into a base. And then the water is going to accept that proton, end up with an extra hydrogen as a hydronium ion, which means it now has the ability to donate a hydrogen back into the conjugate base to turn it back into the reactants. So the water, which was a base, produced a conjugate acid, and the acid produced a conjugate base. So let's use that model for the second one. In this situation, water is going to act as the acid, and I know that because NH3 is ammonia, which is a weak base, doesn't have a hydrogen up front. It does have hydrogens, but it doesn't have a hydrogen acting as a cation. Therefore, it has to be the base. So water is the acid, the ammonia, or NH3, is the base, and you can see that the ammonia, NH3, on the right-hand side turned into NH4+, which means it had to have accepted a hydrogen. Therefore, it is now an acid. So it is now the conjugate acid. The water lost a hydrogen, turned into hydroxide, so it became a conjugate base. So just a little review. The water is the acid, the ammonia is the base. The ammonia turned into ammonium, which is an ion. It is the conjugate acid because it now has an extra proton. And then water turned into hydroxide, which is now a conjugate base. Again, water is amphoteric, meaning that it can be either an acid or a base depending upon what's added to it. All right, so let's just do a couple of examples, give the conjugate base for each of the following. So hydrofluoric acid, or HF, that's an acid. If it's going to produce a conjugate base, that must mean that it's going to lose its hydrogen. And if it loses its hydrogen, that fluorine is going to take on its original ion charge, which is a halogen, so it's a -1 charge. So then the conjugate base is just the fluorine ion. Phosphoric acid, H3PO4, you can only lose one hydrogen at a time. So this acid is going to lose one hydrogen. When it loses that one hydrogen, it has one less positive charge, therefore the whole compound is going to lose the hydrogen and take on a negative charge. So you end up with H2PO4 with the -1 charge because we have one less proton. The hydronium ion is going to turn into just water because it's going to lose that extra hydrogen, and when it loses the hydrogen, it also gets rid of that extra positive charge. As far as the H3PO4 phosphoric acid, that's called polyprotic, meaning that it has more than one hydrogen, and it can actually lose each hydrogen in individual steps. So that H2PO4 minus 1 can then lose another hydrogen and turn into HPO4, but it would end up being a minus 2 charge. So it can lose them one at a time. Okay, so let's just do a couple of examples, give the conjugate acid for each of the following. So if we're looking for a conjugate acid, that must mean that these are bases. So the bromine ion has a minus 1 charge. If it's going to turn into a conjugate acid, it's because it accepted a hydrogen. So if you take a hydrogen with a plus 1 charge, combine it with a bromine with a minus 1 charge, it forms HBr, hydrobromic acid. HSO4 minus 1, if you gain a hydrogen, you're going to lose that charge and end up with H2SO4, which is sulfuric acid. And then the carbonate ion, CO3 2 minus, is going to accept one hydrogen, drop down the charge from a minus 2 to a minus 1 because you accepted that extra hydrogen. And that's really all there is to it.